Hello and welcome everybody to today's lecture on moving average time series model. In the previous video lecture, we saw how to organize time series data, and we also learned how to compute some statistical moments that help us to understand important phenomena, particularly the phenomena of stationarity and ergodicity pertaining to time series data. In today's class, we will study a very particular kind of model known as the moving average model. To make our life easier, we'll begin with the moving average model of order 1. Recall from the previous lecture that epsilon t denotes the white noise, the Gaussian white noise. The moving average model of order 1 will be defined in terms of this Gaussian white noise. In fact, it'll be the weighted sum of the Gaussian white noise sample at this particular time t and the previous time instant. And it'll be weighted by this real constant theta. Plus, we will add another constant term, mu. So y sub t would be defined as mu plus epsilon t plus theta times epsilon t minus 1, where mu and theta are constant. It is known as a moving average model of order 1. Why order 1? Because we are defining y sub t in terms of random variables, in this case the Gaussian white noise random variable, up to the past event, the previous past event, or the time index t minus 1. So that is why this is an order 1 model. Now, what are the properties of the moving average model of order 1? Well, we define them in terms of the statistical moments, and we will begin with the first moment, which is the expected value, which is a linear operator. So we would just distribute the expected value across these terms on the right-hand side. So we will be left with mu, which is the expected value of mu. And then because the expected value of the white noise random variable is 0. If you recall from the previous lecture, expected value of Gaussian white noise random variable happened to be 0. So this is mu, which is independent of time, so that's good. Likewise, we could define the second statistical moment, the statistical moment of order 2, which is variance. And again, we could distribute the calculation of the variance to each of these three terms. So variance of mu, which is a constant term, it doesn't vary, so this is 0. Variance of epsilon t is sigma squared, because that's how we defined the white noise process, remember? Sample from a normal distribution of mean 0 and variance sigma squared. So we have this sigma squared, the second term. And then variance of some constant times the random variable, just the constant square times the variance of the random variable, which is something that we have seen earlier in the class. So that turns out to be theta squared sigma squared. So variance of y of t is just this constant term 1 plus theta squared times sigma squared, which is again independent of time. The first order covariance can be computed by taking the expected value of y sub t minus mu times y sub t minus j minus mu, which is how the autocovariance function is defined. To calculate this, we will just take the mu from the right-hand side and take it to the left-hand side. So yt minus mu would be epsilon t plus theta times epsilon t minus 1. So we'll write the first, we will write the first of these expressions as the epsilon t plus theta times epsilon t minus 1. The second term will just replace t by t minus j, so we'll have epsilon t minus 1 plus theta times epsilon t minus 2. Remember, j here is just 1, so j is equal to 1, so that's why we have epsilon t minus 1 plus theta times epsilon t minus 2. So once we have rewritten these expressions, we'll multiply the two terms, we'll multiply these guys that I've highlighted, and we'll have a bunch of quadratic terms whose expected value we need to compute. Again, expected value being a linear operator, we'll distribute the calculation of the expected value to each of these, across each of these terms. And after some simple algebra, this will reduce to theta times sigma squared if you do the calculations right, of course. The only fact that we have used to simplify this result is that the expected value of epsilon t times epsilon tau is actually equal to 0 for all t not equal to tau because of this condition here. Actually, there is a small typo here. This should not be t minus tau, it should be just tau. We're just using the third property of the Gaussian white noise, which is this property here. Okay, so that's the result that we have used to simplify the calculation of gamma sub 1 of t. In fact, all the other autocovariance functions, gamma sub 2t plus gamma sub 3t, all those, actually if you do the calculations correctly, will turn out to be 0, so we don't have to worry about them. So what does all this tell us? It tells us that the mu's and the gamma j's are constants. The definition of gamma j implies that gamma j is symmetric, which means the moving average model of order 1 is stationary. Additionally, the autocovariance function is absolutely summable because gamma naught plus gamma 1 is a finite term and all the other guys are zeros. So this turns out to be a finite number. So this absolute value of gamma j is absolutely summable, which implies MA1 is an ergodic process. That is to say that we can replace the ensemble averages by time averages. So that's good, right? We have both the good properties that we require. Likewise, we could also find the autocorrelation function, which is nothing but the autocovariance function normalized by the gamma naughts. And by definition, the absolute value of rho j would always be less than or equal to 1. In this case, that is the moving average model of order 1, rho 1 turns out to be this constant theta over 1 plus theta square. All the other rho j's are 0. So that's all about the moving average model of order 1. Likewise, we can have a higher order moving average model if we continue summing the weighted Gaussian random variables up to order q, or term q. So in this case, we would have y sub t equals mu plus epsilon t plus theta times epsilon t minus 1 all the way up to theta q epsilon t minus q, but all these thetas are real constants, and the epsilon t's, like before, are the Gaussian white noise. The calculation of the statistical moments would follow thusly. Expected value of yt would be just the constant mu because all the other terms would be 0. The gamma j's would be 1 plus theta 1 square plus theta 2 square all the way to theta q square times sigma square. And all the higher order autocovariance function greater than q, the autocovariance function would turn out to be 0. And this implies that the moving average model of order q is also stationary and ergodic. Right? In the next class, we'll actually do a particular numerical problem on moving average model of order 2, so you'll know how to apply all these concepts to an actual problem model. Right? So please be patient until the next video lecture. We'll actually see a concrete example. We will also begin next lecture by looking at a moving average model of order infinity, which means that these terms on the right-hand side would continue to infinite number of terms, and we'll see how that would relate to another model, which is an autoregressive model. Looks completely different, but there is a direct correspondence between the moving average model and the autoregressive model. But anyways, all that for next class. Until then, I would advise you to review the concept that we have learned so far, and that's all that I have for you today. Thank you.